Welcome to Unit 13, Inductors, Part A, Structure and Types of Inductors. In this video, you'll learn to describe the basic structure and characteristics of an inductor, identify various types of inductors, and to calculate the self-inductance of an inductor. The basic structure of an inductor is a length of wire formed into a coil. When current passing through the coil, magnetic field is developed around it. Inductance is the property of a wire coil to oppose any change in the current going through the coil. A coil used in this way is called an inductor or a choke. This diagram shows that magnetic field is developed when a current passing through the coil. Such phenomenon is called electromagnetism, which has been covered in a previous unit. The symbol for an inductor is this. L stands for inductance, and we will discuss about it later on. If both the magnet and the coil are stationary, there will not be any change in the flux linkage to the coil, and there will not be induced voltage across the coil. Similarly, when a constant current flows through the coil, only stationary magnetic field will be generated. There will not be any change in flux linkage to the coil, and no voltage will be induced across the coil. However, if the magnet is in motion, there will be change in the flux linkage to the coil, and there will be induced voltage across the coil. If we increase the current continuously, the magnetic field around the coil will increase and expand continuously too. The changing flux in the coil will induce a voltage across the coil. According to Lenz's law, the polarity of the induced voltage will oppose the increase in current. On the other hand, if we decrease the current going through the coil continuously, the magnetic field around the coil will decrease and collapse continuously too. The changing flux in the coil will still induce a voltage across the coil. According to Lenz's law, the polarity of the induced voltage will oppose the decrease in the current. This property of the coil to oppose any change in current through it is called inductance. Let's recap and develop the learning points further. When a current passes through a coil, a magnetic field is developed. If the current changes continuously, the magnetic field around the coil will also change continuously. According to Faraday's law, a constant changing magnetic field can produce an induced voltage across the coil. And according to Lenz's law, the polarity of the induced voltage is in a direction that opposes the change in the current. This property of the coil to oppose any change in the current through it is called inductance, or self-inductance. It is referred to as self-inductance because both the changing current and the induced voltage occur on the same coil. To describe that precisely, the coil produces the induced voltage as a result of a change in the coil's current. The unit of inductance is Henry, represented by a capital letter H. From Faraday's law, we can deduce this formula to calculate the self-induced voltage from the self-inductance and the rate of change of current in the inductor. For example, the induced voltage across a 1 Henry inductor with a current changing rate of 2 amperes per second is equal to 2 volts. A capacitor stores energy in an electric field created by a voltage difference. An inductor stores energy in a magnetic field created by a current. The formula to calculate the energy stored in an inductor is given as this. W equal to half Li square. For capacitor, we have a similar formula. W equal to half CV square. Inductance L can be calculated by this formula. N is the number of turns of the coil. Mu is the permeability of the core material. A is the cross-sectional area of the core. L is the length of the core. Take note that L is not the length of the wire coil. L is the length of the core of the whole inductor. You have learned about permeability in the units of electromagnetism. Let's have a recapitulation quickly. Permeability of a material determines how easily a magnetic field can be established within the material. The permeability of vacuum, free space and air are denoted by μ0 and has a value of this. The permeability of all ferromagnetic material is higher than μ0. The relative permeability μr of a material is equal to the permeability of the material μ divided by the permeability of vacuum μ0. So μ is equal to μr times μ0. Let's check up this simple example to apply this formula to calculate the inductance. The number of turns is given to be 350 turns. The permeability of the material is given as this value. Cross-sectional area A can be calculated from the radius pi r squared. But the radius is given in unit of cm. We need to convert it to meter as this. For the length, it is given to be 1.5 cm, so we convert it into SI unit 0.015 meter. Plug in all the data. The inductance can be calculated to be 40 millihenries.